Hey, basic calc students, this is going to be our day 25 notes on something called Newton's method. And Newton's method is really cool. It's actually a way that we can approximate zeros of a function. It's a way for us to approximate roots. So I know at the start of your notes, I gave you this blank set of axes. If you can draw in a function that looks similar to mine, call it y equals f of x. What we're going to do is we're going to see how does Newton's method work to approximate this root right here for the function f of x. And what we're going to have to do in order to figure out where that root is located is kind of make an initial guess. So if we were to look at this, let's say on our calculator, and we can kind of see it crosses, in between two integer values, maybe I'll make a guess and I'll call this guess x1. And what we're going to do is we're going to trace up to the curve, and we know that that hits at the point x1 comma f of x1. And what we're going to do is we're going to find the tangent line at that point. So we're going to find the derivative and write the equation of that tangent line. And what we see is that the tangent line here is going to wind up hitting the x-axis at a certain location. We'll call this location x2. And whatever that x-intercept is, you're going to use this as kind of your next guess. And notice how that next guessing place is even closer to the root. So what you're going to do is you're going to, from there, trace down to the curve, draw the tangent line at x2 comma f of x2, which now should look something like this. And you'll find that this tangent line hits the x-axis at a certain location. And the location of that is at x3. And look how we got even just a little bit closer. And, we're going to kind of do this whole thing where we're like ping-ponging back and forth. Is how you kind of describe the motion here. So we're kind of going on opposite sides of the root, and we're getting closer and closer and closer and closer. And eventually, through a process, we'll converge on that root right there. Right? If I were to then trace up to the curve and draw this tangent line, it's going to squeeze in and it's going to get really, really close to that root. And this becomes what we are terming an iterative process that can be modeled using a recursive sequence. So after we run through some iterations of Newton's method, we'll find a really solid approximation for where that root is located. So how are we going to do this? Well, first thing I want to talk about is what is the equation of that initial tangent line there? We know that the slope of the tangent line is going to be f prime of x1, and that we're finding the equation of the tangent at that point, x1 comma f of x1. So therefore, in point slope form, the equation of the tangent line is y minus f of x1 equals f prime of x1 times x minus x1. So using this point, this slope, we should be able to come up with that fairly easily. So what are we trying to do? We're using the equation of that green line up here, and we're finding the x-intercept of that line. And that then becomes the location of our next guessing place. We find the equation of that tangent line, use the x-intercept. So what we're going to do is let's talk about how do we find the x-intercept of this tangent line. We're going to set y equal to 0. And then we're going to wind up solving for x, because this value of x right here is representative of the x-intercept. So when you plug in 0 for y, you get negative f of x1 is equal to, over here, I'll distribute f prime of x1 would get multiplied by x, and then also by x1. So from there, remember what I'm trying to do is I'm trying to isolate x. So I'm going to add this term to the other side. Okay. So therefore, x1 f prime of x1 minus f of x1 would equal on this side x times f prime of x1. And then that last and final step is just dividing by f prime of x1. And when I do that on both sides, I'm just going to write this with x on this side. So the x-intercepts would be equal to, well, if I divide this by f prime of x1, it's just x1 minus, and then this would be the ratio of f of x1 over f prime of x1. And that second x-intercept of this tangent line is what I denoted up here as being x2. That's our next guess that we would use to then write our tangent line at. So what we can do is we can then kind of make some connections that if I repeat this process again to eventually get to the third guess at x3, x3 would be dependent on x2 minus f of x2, and then the slope at x2, f prime of x2. So the relationship among these subscripts in general eventually winds up becoming the following. So in general, the formula for Newton's method will be x sub n plus 1 would equal x sub n minus f of x sub n over f prime of x sub n. Okay. So if we run through this model a couple of times, we should be able to, again, kind of ping pong back and forth around the root and eventually become really, really close there to approximating the root of that function. Okay, so we're going to see how we can put this into practice on the next page. Here's what it is in general again, written at the top. And we're going to use this to calculate 3 iterations of Newton's method to approximate a 0 of x squared minus 2. Now, the nice thing about this is that we're going to use a function that we know the zeros of pretty clearly. So if you were to sketch x squared minus 2, which looks something like this, knowing what those roots are, we know that there's a root that occurs somewhere between 1 and 2. So what we're going to do is we're going to use x equals 1 as our initial guess. Okay, that's kind of your x1 value. So let's use x1 equals 1 as our kind of initial guess. And then we're going to see, based on running through this Newton's method iteration, how close we can wind up getting to the actual root there, right? It would be the slope of the tangent line at x equals 1. Wherever that hits the x-axis, that x-intercept, draw the next tangent line, and you're going to find that we're kind of bouncing back and forth and converging upon that root. Okay, so for our first iteration, where n is equal to 1, the x1 value that we're choosing as our guess is 1. And then f of x1, in this case, if you plug it into the function, 1 squared minus 2 is negative 1. In this column here, we're going to need to know the derivative. Derivative of x squared minus 2 is pretty easy. It's just 2x. So therefore, f prime of 1 is going to be 2. And then to calculate x sub n plus 1, we're going to use our Newton's method formula up here, which is x sub n minus f of x sub n over f prime of x sub n. So you can see how kind of all of this information really leads us towards that last calculation of doing x sub n, which is 1, minus the ratio of what you have here. So 1 minus negative a half is the same thing as 1 plus a half, or 1.5. Okay. So that's the new x-intercept that we would find the tangent line at and then kind of start the process over again. So our second guess for x2 is 1.5. Okay, take what you had in the last row and kind of repeat the process. So what's f of 1.5? 1.5 squared minus 2 is a quarter, or 0.25. The derivative at 1.5, 2 times 1.5 is 3. And then if we do our calculation for x sub n plus 1, it would be 1.5 minus the ratio of these two, which turns out to be 1.416, repeating. And again, you can use the calculator, of course, to do some of this. We're going to be relying pretty heavily on the calculator in a minute. But then the last iteration would say, okay, take what you had in the last step. That's your new x-intercept. Okay. If you plug this into the original function, you get 0.006945 is the function value. So, I mean, look how close we're actually getting to the root now at this point. We started at a y value of -1. We decreased to 0.25, or I guess physically increased, but we decreased our distance from 0. And now look how close we're getting here. That's kind of a good indicator. We plug it into the derivative. 2 times that would be 2.83 repeating. And if we do x sub n minus this ratio right here, you get 1.414216. ... Okay, so look at the change that happened from our n equals 2 guess to our n equals 3. There's not really a huge change there, is there? And that's what we'll find happens fairly quickly using Newton's method, that this process of eventually getting down through this recursive sequence, it's going to start being really tiny changes from one value of n to the next. So if we actually compute the roots, we know what they are, right? I mean, x squared minus 2 equals 0 would give us roots at plus or minus radical 2. So radical 2 is about 1.414 ... And look how only 3 iterations got us pretty close. Okay. So we only computed 3 iterations of Newton's method. And we're already close. Okay, so if I had gone a few other iterations out, I bet we're going to see very tiny differences in these decimal point values. Okay, and get something really, really close to what we know the actual root is located at, which is at radical 2. Okay, let's see how we can use Newton's method in this next example to approximate the zeros of y equals 2x cubed plus x squared and then minus x plus 1. We're going to continue this process until 2 successive approximations, okay, one after the other, differ by less than 0.0001. So we want our approximations to differ by less than 1/10,000th. And that sounds pretty tiny, a pretty tiny difference, but we'll see actually it happened pretty fast. Okay, I'm going to start with y equals here. And I'm going to type in the function 2x cubed plus x squared minus x plus 1. And what we want to do is we have to graph this first to get our initial guess. Okay. So if we do maybe a quick zoom 6 here, we can see that this has a root fairly close to -1. Okay, it's not an exactly -1, but it seems like that's going to be a good initial guessing location. So based on the graph looks something like this. Okay. I say we make our first guess for x1. We'll call that -1 in this case. Okay. So what we're going to do is in y2 in the calculator, we could find the derivative of that function pretty easily, but we can let y2 represent the derivative of y1. So in y2, we're going to do math 8. The derivative with respect to x of y1, alpha trace gives you y1 there of x. And having these individual functions stored into y1, it's going to be pretty useful because if you quit the home screen here, remember that Newton's method is x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So the function value is what we have stored currently in y1. And the derivative of that function value is what we currently have stored in y2 on the calculator. So on the home screen, how can I use the home screen to start evaluating some of these iterations? What I want to do is I want to store my initial guess in x. So this value of -1, we're going to store that as x using the stow function. Okay. So if you go to, on your calculator, -1, and then if you guys haven't used store, I use it in pre-calc and algebra 2 a little bit here, but hit store, and we're going to store that as the value of x. Hit enter, just so that we have that stored in there. Okay, so from there, what do I want to do? I want to take my value of x, which is -1, and I want to subtract f of x1 over f prime of x1. And without even doing all those calculations, we already have that typed into y1 and y2. So what we're going to do is we're going to do that x value minus the ratio of y1 over y2. And whenever that is, then that gets stored in X, and we kind of repeat that process again. So we'll be able to kind of keep track of what's happening at n equals 1, n equals 2, n equals 3, and so on and so forth, okay? So let's see what winds up happening. If I do, with my X value stored there of -1, X minus, and then we'll do maybe a fancy fraction here, y1, oops, sorry. I'm gonna go to vars over to y vars, enter for function, enter for y1. Same thing in the bottom, vars, y vars, enter for function, enter for y2. Okay, my new value here is 1.33331. Okay, and I want to keep going with this until we find that the difference between two approximations is less than 1/10,000th. Okay. So remember, now this is my new guess for the next step. So now I have to store this in X. Okay. And now that that's stored in X, I want to do X minus y1 over y2 again. So you can actually just copy paste that. And now my new guess based on this last iteration is -1.2433 86229, like that. Okay. And then I want this to be my new value of X, don't we? And there's a way we can shortcut this that I'll show you in a little bit. Okay. So store that in X and then repeat the process. Let's do X minus y1 over y2. And notice how our iterations are starting to really narrow down on the actual root here. Here's the next guess. Do these differ by less than 1/10,000th yet? Out to the 4th decimal place? Not quite. Okay. So now store this in X. Okay, repeat the process. We get for n equals 4, the 4th iteration, -1.233751,941. The difference there is not quite less than 1/10,000th, but we're so close. I think if we just do one more, n equals 5. So store this in X one more time. Run our approximation. -1.233751,929. I mean, yeah, out to 4 decimal places there. These differ by less than 1/10,000th finally. Okay. So how many iterations do we need? We needed a total of 5 iterations to kind of guarantee that we're within 1/10,000th. But if we were to actually calculate the root, we should be able to find that the calculation of this root is really, really close to -1.23375. In fact, let me just go back and confirm that real quick, that if I go to the graph, we can do second trace, calculate the 0, and go to the left and right. The actual root is at -1.233752. I mean, yeah, look how good we are with our running of Newton's approximation here. Okay. So kind of a cool process. Let me show you how we can shortcut it a little bit rather than keeping on, storing the new value in X every single time. The last thing we're going to do is take a look at an extension of Newton's method, which is being able to find an intersection between two functions. And we're looking at that specific intersection that happens between 0 and pi over 2 for this example. So to estimate the intersection point between two functions, we know that we can think of this as an application of subtracting the two functions and comparing it to 0, right? When the two functions intersect, the difference between them would be 0. So if we let the function f of x equal the difference tan x minus 2x, approximating the root of this function, the difference in them, is the same thing as finding the point of intersection. Since, again, the difference of two functions equaling 0 is where they intersect. We can use Newton's method if we actually just subtract those two functions. And again, we're going to take a look at this when we use our approximations that we'll do in 1 second here. We have to make an initial guess, though, right? Okay, just to save us some time, I'm going to tell you, if you look at this on the calculator, I'm going to guess x equals 1.2 is kind of our initial guess. So 1.2 has to get stored in X. And what we then did in the last case is we took that value of X And with our functions in y1 and y2, where y1 is tan x minus 2x, y2 is the derivative of y1, every time we got an answer, we stored that as the new value of x. So if you do this initial stow function of what your initial guess is, you can then take each of these calculations that we were doing, store those in x, and then I'll show you actually how the calculator steps get much, much easier. Okay, but remember, y1 you're typing in tan x minus 2x. In y2, you need the derivative with respect to x of y1 at x equals x. Okay, so go ahead and enter that. Make sure you're in radians. Okay, minus 2x, y2 is my derivative, math 8. Okay, so now I've got that typed in. All right, if I quit this screen, clear this out, I needed to store 1.2 as my initial guess. So 1.2, store that as x. And then from there, if that's my initial guess, like I was saying, instead of taking this result and always storing it as the new x value, we can just enter this in as parentheses x minus alpha y equals vars y vars, enter for function y1, and then vars y vars, choose y2, and then store that as x. Okay, so every time it runs through an iteration, it stores that as the new value of x, and then plugs it back in over here and runs through it, and then stores that as the new value of x. If you hit enter, there's the next approximation, 1.169346. Hit enter again, just keep hitting enter. It's gonna keep running through that approximation. Now the new one is 1.1656. If I run through that again, 1.16556. Okay, so we've now been able to run through a couple of iterations here, and you can see that we're already differing by less than 1/1000 or 1/10,000. Sorry. Okay, so if you are able to enter it this way, and then just keep hitting enter, enter, enter. Okay, that's going to run through all the iterations that we need. And it turns out that the best approximation for the point of intersection here is approximately 1.16556. Okay. All right, so next time we're in class, we will definitely do some more practice with making sure we understand the calculator steps associated with this process and understand Newton's method in general. The last thing I'll ask you to do quickly before you head off for today is maybe just try a quick curve sketching, make sure that we're still able to successfully find intercepts, critical points, inflection points. Make a really nice sketch of this for me, and we'll go over this sketch in addition to any other Newton's method questions you have next time I see you in class. All right, that's it for today. Have a great rest of your day.